right. Well, good morning, good afternoon, everyone, and welcome to today's Exploring by the Seat of Your Pants event. My name is Joe Grabowski, and I'll be your host for today. We are down to our last few days before the holidays. I'm sure everyone's getting really excited in the classroom, but we still have more action coming your way. So we've actually got a few more events this week, and then several events coming up next week, including a live hangout with astronaut Jessica Meir right before the holidays. So you don't want to miss that. We just had to shift the time of that slightly. But you'll see that coming up on the 18th. And then we'll have one more newsletter come out over the weekend. So you can also visit exploringbytheseat.com to figure out what's coming up, how you can get in on the action with your classroom, whether it's live or catching those recordings. So today we are going to spend a time with someone who I would call a veteran of Exploring by the Seat of Your Pants. We've been so lucky to have Bobak Ferdowsi join us for many events, especially during our space exploration months, and share some of the really cool things that he does with NASA's Jet Propulsion Laboratory. So right now he is the payload manager for the NISAR Joint Observation Mission with India at NASA's Jet Propulsion Laboratory. But prior to that, he's had launch, cruise, and approach engineering lead and flight director on Mars's Science Laboratories Curiosity, science planner on the Cassini mission, flight software, product line system engineer, and Europa Clipper Mission Planner. So he's had his hand in a lot of really cool robotic missions exploring beyond our planet and into our solar system. So I'm going to grab Bobak from a backstage right now. Here we go. Hey, Bobak, how you doing?
Hello, good to see you.
Yeah, great to see you. Great to have you hanging out with us live today in sunny California. I would like a little bit of that sun here. It's
It's pretty good.
little snowy here in Canada, but I guess it's better than a green Christmas. So we'll take it.
Yeah,
All
I'm
right.
jealous.
All right. Well, we've got classrooms joining us in Canada and the US today, so they're going to fire away with questions when the time comes. I see groups in Edmonton, Alberta saying hi already, in Maine, in Tucson, Arizona. So hey to those groups saying hi. We've got some groups backstage we'll bring in as well during Q&A time. But Bobak, we'll let you take over for a little bit and share.
Awesome. Well, thank you. Yeah, I'm really excited because I've been so busy because we've been working on this NISAR mission, which just launched, and I'll get into that a little bit. I'm Bobak. It's really nice to be here. Thank you guys. Thanks to Joe also for always finding time for me and working around my busy schedule to make this happen. So I'm excited. This is me as a kid. I just wanted to put that in context. I wanted to be an explorer since a young age. And what I do now is do that through the magic of robots. I was fascinated by science fiction growing up. I read a lot of books, Arthur C. Clarke and Isaac Asimov, and watched a lot of Star Trek and Star Wars, and said, I want to be part of that future. Like, I want to go see space and explore it, and I want to learn about it. And this is me, of course, as an adult, pretending to be Spock from the original series of Star Trek with some of my friends here. We had a great time. I still do stuff like this, but very much science fiction is still a part of what makes me motivated and excited, because I feel like so much of my day-to-day is still working on these things, and it's really hard to believe that I get to work on spacecraft that are at other planets or just things in space in general. So it's really fun. This was taken shortly after I got hired here. So this is maybe like month 2 of me at JPL. This was January of 2004. And just days earlier, we had landed a pair of these rovers called the Mars Exploration Rovers on the surface of Mars. This was Spirit and Opportunity. These were 2 rovers that lasted for a very long time. Opportunity for 14 years, a pretty good amount of time on the surface of Mars. Solar panel rover. You can see the size of this just to give you some context of how big a rover can be on Mars. And this was kind of so exciting for me because these things were landing just as I got there. And I thought, like, this is what every day is going to be like at NASA. We're going to be just putting stuff on Mars all the time. Turns out it would be a little bit before we send the next thing to Mars, but I got to work on one of them, and that was the Mars Curiosity rover. NASA's Jet Propulsion Lab, where I work, is predominantly for robotic spacecraft. So that's really the main focus of what we do. We don't do a lot of human spaceflight. We do a little bit of interaction with human, meaning like the robot-human interaction, but really it's about us that get to go to places that many of us can't go. My first job at JPL was working on the Mars Science Laboratory, which is a rover as well, a little larger than the one that you saw me with in the photo. This one is about this, the one that I worked on is about the size of a small like Mini Cooper or golf cart. This is our test facility that I was working in a lot of the time. So we have to basically, they're really designed to be in space, and so it's really hard to, uh, you know, to do that easily. In this case, I'm working on the rover's compute element and the entire buildup of what it would be like in space between Earth and Mars. And so at the left there, you can see one box that says Oliver or RCE. That is a computer, one of the two computers inside the rover that would have been there that would have been controlling the spacecraft. And the entire 4 racks that are behind me basically are simulation and support equipment, meaning because in space we actually have things like stars to look at or temperatures to sense or thrusters to fire. This system out there allows us to basically simulate all of those things for the hardware. So in here we could stimulate like, oh, I'm looking at the sky, and therefore our space, our rover that's tucked away that's processing the mapping of the stars can actually tell those things. And so I did this for about 8 years before we actually got to land a rover here on Mars. And that's this rover here. That's the Curiosity rover. This was taken shortly after arriving, so it's still very clean and crisp, and there's very little dirt on it. The little dirt that you do see is actually mostly kicked up by our own engines during our landing. Curiosity has now been operating for 13 years on the surface. So I'm really proud to be able to have been part of something like that. And again, we expect it to last for several more years at least. It's been exploring Mount Sharp, which is the rise kind of mountain that you can see behind it. And that's we basically landed a little safe distance away from it so that it was a nice big flat safe landing site. This area that we landed in basically is Gale Crater. It's a big flat, relatively flat area. There's evidence in Gale Crater, even before we landed, that there was water there in the past. And so we chose it because we thought it would be a good environment in which to study the habitability of Mars. Basically, could Mars have supported life? And the answer, within a couple of years that we found is yes, right? There is a time in Mars's history in which Mars could have supported life. We can't look directly for evidence of life. That's what something the next mission's Perseverance and eventually a Mars sample return mission would try to accomplish, which is to gather sample and bring them back to Earth to look for any past evidence of life. But Curiosity chugs away. One of my favorite things that you can see in this picture, besides, of course, Mars, and the rover, is in the pattern on the treads here. If you look a little carefully, and I'll move my mouse here a little bit. These little dotted or slotted areas on the wheels, and then you can see the pattern down here. This was a little Easter egg that we hid on the rover, which spells out JPL as we drive across the surface of Mars in Morse code. So little Morse code bits, we're leaving a small trail. They'll get wiped away with time and wind and everything else, but for a little bit in all of our pictures, you get to see the JPL kind of written in the sands of Mars. I want to show you guys this. This is from Perseverance. This is the follow-on rover to Curiosity. We didn't have cameras on Curiosity to do this, but I thought I'd show you guys what it looks like when we land on the surface of Mars. And I'll try to narrate this a little bit for you guys. So, and first, top of the atmosphere, we are in a heat shield, but then we deploy a very large parachute. This is what we call a supersonic parachute, meaning that at the time we deploy this, we are traveling faster than the speed of sound. And so it's a special design, a parachute that's required. That also has a little Easter egg into it, which is the banding on there spells out JPL again, and also gives the coordinates of JPL in terms of latitude and longitude. Once we slow down from about, I think about 1,000 miles an hour down to a little less than a couple hundred miles an hour, we are going to deploy our heat shield, and that falls away from the rover surface there. And at this point, we can start detecting the surface of Mars. So this is our cameras doing the detection, but there's also a radar system that's measuring the distance to the surface, and is also measuring the velocity horizontally. So how far are we moving along the surface of Mars at the same time? Our goal, of course, is to land as softly as possible so that we don't damage anything of the rover as we land. And so the system here is just trying to get a good lock. Here you go to the crater that we're trying to land in, and the river delta there at left. I will, oops, I did not mean to restart that. Let me come back here. So this is right here is the delta that you can see that's flowing into the Jezero crater, which is, again, one of the reasons why we chose this. Perseverance has a little bit of advanced technologies as well. So as it's landing, we do a little bit more smart calculation of the landing site and try to pick some better locations. All right, I'll let this play out for a second. So you can see we're still wobbling around on the parachute at this point. So this is just keep slowing us down until we can get above the surface and use the engines to propulsively lower ourselves. All right, so we've separated from the parachute and now we're doing a propulsive maneuver, and we're still very bundled up. We're trying to kill our horizontal velocity, meaning we're still traveling horizontally, and we're trying to start traveling vertically. So you'll start seeing that in a second as we lock onto the surface. There we are, nice and locked. And now it will separate the rover from the jetpack. And the jetpack will basically hover above while we slowly lower the rover to the ground. And you're going to see that here at the left. So there's the hovering jetpack and the rover slowly being lowered to the ground, kicking up a lot of dust as we're doing this, of course. So that's pretty exciting. That was the first time I got to see it. So I knew how it worked on Curiosity, but it was really awesome to watch the Perseverance landing and see it happen. Um, so I worked on Curiosity for about a year after landing, and then transitioned over to the Europa Clipper project. This is a mission to Jupiter's moon, Europa. It's one of the 4 large moons of Europa that, with a pair of binoculars or telescope, you can see pretty easily. They're called one of the Galilean moons because Galileo, with the technology available to him, like a telescope, was able to discern that there were 4 moons that were orbiting Jupiter, and that was his first evidence that that the Earth was not the center of the solar system. In fact, that other objects that other objects could orbit around things other than Earth. And Europa is fascinating to us in part because of a couple of missions that have traveled there. The Voyager missions traveled past this very quickly, and then we had a Galileo mission that was sitting at Jupiter for many years, and it took many images. This is a processed image from the Galileo missions of the surface. And one of the things that we kind of see here that's really fascinating is it's got relatively few craters, right? For a moon that's around the same age as our moon. Our moon is covered in craters. You see a couple of craters here, but you don't see a lot. What you see instead are these large cracks, which indicate an ice surface that is shifting. That is moving and breaking and then reforming. And that smoothness also tells you a little bit about the fact that, right, there probably were, we know that there were asteroids flying around the solar system, there still are, that would be impacting Europa. And if it didn't have a surface that sort of changed over time, that wasn't being resurfaced, it should be covered in crater marks. So these clues lead us to believe that there is a process on Europa by which this ice that's at the surface is melting and being resurfaced. And then when we flew the Galileo mission by there, we were able to detect a magnetic field, not that the Europa is the source of the magnetic field, but it was resonating with the magnetic field of Jupiter. That's very similar, like if you've walked through a metal detector at the airport or somewhere like that, if you have metal on your body, the metal detector is actually putting out a small magnetic field, and it's going to pick up on the resonant magnetic field from the metal that you're wearing on your body. And that's what gives the alarm if it detects significant amounts of that. And our Galileo mission was able to detect a kind of resonant magnetic field at Europa. That means that something is moving underneath the surface of Europa, whether it's electrons in this case, but in order for that to happen, you have to have sort of, and so we believe that there is a ice shell on Europa, and then below that is an entire ocean, potentially hundreds of kilometers deep. And that there's warmth and water and chemistry there that all could be the ripe environment for life to arise again. So a couple of years ago, we launched the Clipper mission on its way to Jupiter, eventually to orbit Europa, and that flew by Earth again and Mars, and so now it's on a trajectory out um, to Jupiter. So it's trying to gain acceleration to get away from our sun to get there. Still a few more years before it gets there. And eventually it'll look something like this, where we'll carry the satellite over the surface. We get down about 25 kilometers of the surface of Europa. So we can take very precise measurements and images, and also sense a lot of the materials that might be coming off of plumes, right? So where these cracks are forming, we hope that there's evidence of water being kind of sort of cryo volcanism events. And so you can kind of get some water in there. We can fly through the mist of that and detect if there's any sort of chemistry in there that could be the resources that life would need to survive. And then I moved on to my current mission, which is the NISAR missions. It's an acronym of acronyms, which is very popular here to do acronyms. So it's NASA, ISRO, which is the Indian Space Research Organization, synthetic aperture radar. We built a large part of it here at JPL, and then flew this part of it that you can see at the right out back to India to be integrated into the spacecraft. We have to wear these clean room facilities whenever we're there, because our satellites are sensitive to things like hair and dust and other things going on them. And so it's critical that we don't introduce any sort of way for hair to land and short circuit something. So these are again, delicate instruments. So this is a very bundled up version of the satellite. Because we launch on launch vehicles, we have to be origami kind of folded down to our smallest possible size, so we fit on top of the rocket. And then in order to reach our full potential, we actually have to deploy a lot of this hardware and get it open in space. What's NISAR trying to answer? So we are trying to detect these very small levels of surface deformation, right? Things that would occur with volcanism, with earthquakes, with ice sheets melting and movement of the ice at the poles. We do this every 6 days. We basically are generating a full map, and every 12 days we repeat the exact same orbit over the Earth that we had previously. So every 12 days, we can precisely tell you that this part of the Earth has moved by this much. And there, I'll show you some examples of that in a couple of charts. We've got a couple of radars actually on here. So there is an L-band radar and an S-band radar. And this is a very large reflector. This is 12 meters across. The surface area of this is approximately the size of a 2-bedroom apartment. So if you think of the amount of floor area you'd have in a 2-bedroom apartment, that's about as big as our reflector here. That's this part. So that's this part up here. That's the reflector. So this is a partnership between us and India to do this. And I think the ultimate goal here is really a lot of things. But again, one of them is to understand our biomass situation, right? What is the things like forestation, agriculture, soil moisture, which allows us to help inform some of the agriculture. So there's already farmers and people like that who can use data sets coming off of these missions to help them inform how much water is in these crop regions, and then how much additional water might be needed to augment that. And then things like ice melts, which we can now detect at the poles. When the presence of earthquakes and things like that, we can actually look for the amount of changes in those areas pre and post. Some of those can actually inform decision-making policies, meaning that if you see certain areas, you can deploy resources to those areas post-earthquake. We launched this only 4 months ago, so very recently. And I got a couple of camera images off of the satellite as we are deploying, and I just talked to them very briefly. So here at left, here at left here is this is the structure that you saw back here. That's this structure out here. So the kind of black and gold thing. That's now sitting out here in space. So this is the Earth. And then we are trying, right before our deployment, so we're deploying this structure eventually. When we get this structure out, it gets out on a big 9-meter boom. That's this segment right here. And then we unfurl the reflector. These are 2 different cameras. They have different angles, but this is the reflector. It's made out of sort of a gold material, so it's reflective to the bands of radar that we're looking at. And then fully deployed, it looks like this. This is looking up from the bottom of the spacecraft, looking up with the reflector. And luckily enough, Vantor, which is an imaging company in space, they were able to capture an image of our satellite. So this is an actual picture of our satellite taken by another satellite in space post-deployment. So you can see the fully deployed reflector, the solar panels on the spacecraft bus. This is the main part of the bus where the sort of support engineering equipment is located. And then this part sticking out here is actually the radar, a lot of the radar hardware. So this is bouncing signals up into this reflector and back on Earth, and then getting the receive bounce back and then detecting it here. So just kind of like a focal, this is right, a focal plane. So if you use like a telescope or whatever, right, this is kind of the lens part, and it's focusing the images back here. What can we tell from this? So this is one of the very first images that we took over North Dakota, and the top there you see the optical image, and at the bottom there you see our radar image. I should note that these are not taken exactly at the same time. So there are some of the changes you might see here are not necessarily because of what we can see in radar versus what we can see in optical, but also because of the seasons and everything else. But we can actually detect, right, for example, what the various things are. And you might ask, how do you do that? Right, it's kind of challenging. And the answer is we're really good at this because we can tell this from data sets that we have on the ground that we can correlate to the data sets that we get in orbit. And radars measure the scatter from a thing. So where here I'm looking at scattered, but in this case, scattered light that's coming back to us. Here we're looking at scattered like radio frequencies that are coming back to us. And we know the relative roughness and what surfaces look like, what they would kind of bounce back to us in various kind of wavelengths. And that allows us to kind of correlate that. One of the great things, though, is this will work whether it's cloudy outside or whether it's nighttime, whereas optical, right, is limited to daytime images and only when the weather is good. So that's one of the reasons why our data set is so valuable, is we can do this 24/7, 365 days a year and provide data for the entire globe. This is one also an early image. So we actually have multiple radars that are imaging, which is why you see these bands in the middle, and they eventually will get correlated together. But that kind of gives you a sense of what it looks like over the Sierra Nevadas and things like that. And then here's another example of how we can decompose images over more urban areas as well. So you can see the types of reflections. These are usually double bounce reflections, meaning that the radar will hit like the building and then the ground and come back to us, or the ground and then the building and then come back to us. So we can tell that the urban areas, for example, versus the non-urban areas. And so again, you can use this large data set very quickly to ascertain the effects of things. Another example that we can tell, which is recent hurricanes. So we can actually we don't actually see the hurricane. And so you might be asking, well, what am I looking at here at left? What you're looking at is actually the hurricane on the ocean. And the winds from the hurricane are causing the ocean swells and waves to occur. And so we get reflection off the wave surface of the ocean that, of course, looks like a hurricane because it's hurricane shaped, and you can see the eye of the hurricane. You can see the outer parts. This is actually the movement of the ocean due to the hurricane. And then at right here, you can see the impacts. So this is an image that we took before the hurricane and afterwards. And then the increased black here is the flattening area, meaning that there's flooding, and we're seeing less scattering of the image. So those are kinds of things that we can tell very quickly with the radar images. So it's up there now today, so I'm really proud of this. That's what I'm currently working on. In fact, today I have to do some more analysis on this. But this is kind of an artist rendition of that. So thank you, guys.
All right. Thanks, Bobak. That's a very cool mission. I know how exciting it must be to see something as you work so long on, see it in space, see it delivering results. That satellite picture was really cool to get that view. So that's pretty special. Yeah. It must just be pretty awesome to see something you've worked on, your team's worked on, and see it delivering and doing what it's supposed to do.
It really is. I mean, I've had the fortune of working on this one for almost 9 years. But like, I think just also being part of a team that gets to do something like that, and then all of us get to I don't know, grow together and have these experiences. In this case, right, a lot of us were traveling to India back and forth. I spent, I think, a total of about 8 months in India in the last 2.5 years. Um, but like, it's just, yeah, really, it's like being part of a family that gets to birth a satellite in this case. And I think it's just really fortunate that that people are interested in, and willing to let us do this work.
Yeah. You mentioned JPL Easter eggs on a few projects. Are there any sneaky Easter eggs on this one?
I think on this one, it's mostly some of the fault protection, which is the thing that we worked on initially, have little references to like movies and things like that. So we have, if we have a time jump, for example, where the GPS time being provided to us seems to be in the past, we call it Back to the Future. We have the tension is too high, which is a reference to the rent is too high meme a few years ago. There's little things like that where we just
Yeah.
called our things on board various names that are kind of
Cool.
references to what was going on at the time we were doing it, designing it.
All right. Well, we are going to have a little Kahoot quiz with our classrooms hanging out with us. And then we'll spend the rest of the time on Q&A action. But I'm going to take a few questions as the Kahoot loads as well, because we've got lots of questions coming in via the chat.
Okay.
But we'll get this onto the screen. So that should be on the screen now. If you want to play some Kahoot with us in the classroom, there's multiple ways you could join. First of all, if you have tech at your seat, maybe you have an iPad or a Chromebook, you could join there. So kahoot.it and then pin number 9530639. A lot of classrooms might not have that one-to-one tech, but if this is up on your screen right now, so you can shout out your answers to your teacher and play along that way. And if you're at home, you can even scan that QR code. I know we have homeschool groups joining us today. You could scan the QR with a tablet or a phone and join that way. So while we wait to see if a few groups come in here and join us, I want to grab a few questions from online. So let's see. Our first question is from a group in Tucson, Arizona, Bobak, and they want to know, what did you study in school that led you to work at NASA?
Yeah, so when I was in middle school and high school, I definitely started getting really excited by things like physics. When I got to college, I actually started as a physics major, thinking I would build more of the instruments. And it turns out I didn't have the patience for it, which is funny for somebody who's now spent two missions, almost a decade on two different missions. But at the time I was, younger, I just thought, oh, I can't do this for very long. And so I transitioned from that into a degree in aerospace engineering. So that core, aerospace kind of encompasses a lot of different things for different people. But for me, it was a focus on software, electrical engineering, and materials. Of the two, I probably use electrical engineering and software the most today in terms of my interaction with spacecraft design. Yeah, and then I ended up getting a master's degree in the same areas, basically, when I moved on that, in an area called system engineering, which is what I do, which is thinking sort of at the big picture level of how satellites or spacecraft should work.
All right. We'll grab one more before we start. This one is from some grade 5s in Edmonton, Alberta. They're wondering, do other planets have tectonic plates like Earth?
Yes and no. So we don't see like evidence of that on Mars, for example, of tectonic plates, but you have similar kind of things like on Europa. We hypothesize that there are places that would have tectonic plates like Earth. We just don't really necessarily have them in our neighborhood.
All right. We've got a good crew here ready to play some Kahoot, so let's get it started. There are true and false. There are multiple choice. The quicker you put in the right answer, the more points you're going to get. So let's get this up here, counting us in. We've got a nice, easy warm-up question to start. Where is NASA JPL? Is it in Texas, in California, in Florida, or in Maryland? So all of those places, all of those states have NASA facilities, but in which one would you find NASA JPL? In Texas, in California, in Florida, or Maryland? You have 12 seconds left to lock something in. Should remind you, though, the quicker you lock in your answer, the more points you're going to get. All right. Good job, crew. It is in California. Let's go to our scoreboard. Octopus is holding down that top spot. We're going to go to some true or false action. NASA JPL focuses on human space flight missions. Is that true or is that false? NASA JPL focuses on human space flight missions. You have 11 seconds left to lock something in. Whether this is true or false, that JPL focuses on human space flight missions. Oh, we had a few more go true, but the falses are correct. It is more the robotic missions, the rovers to Mars, things to look back at our planet, missions to Jupiter and places like that. So yeah, they focus on the robotic missions. The whimsical fox steals that top spot. Another true or false coming your way, that Curiosity has been sciencing for 13 years on Mars now. So what do you think? Curiosity, we know it's there. We know it's there for a bit of time now. Hasn't been doing that sciencing for 13 years now. Got a few more seconds, 3 more seconds. All right, good job, crew. That is absolutely true. Bobak, was there an estimate for how long the engineers thought it would last for? Like, what was this is how long, but we're going to over-engineer it, so hopefully it goes longer.
Yeah, the warranty, the warranty that we offered was 1 Martian year, which is about 2 Earth years.
Okay.
And that's the part we guaranteed it kind of to work, right? We test almost everything to about 3 times that, meaning we test to about 6 years here, or sometimes accelerated testing. And then I think one of the unique things is Curiosity carries a nuclear power source as its energy, or where it gets energy from. And so that is degrading over time, just as a natural process of the half-life of the plutonium on board. And so I think we thought initially around the 10-year mark where it would be very difficult to get enough power every day out of it to keep doing meaningful science. But it turns out, there have been improvements, and the team is getting better and better and more efficient. And so they've been able to kind of keep squeezing more years out of that nuclear battery on board.
All right, very cool. Well, we know you guys are good at what you do. You just have to look at something like Voyager, which is over 40 years now, and still sending back data. That's pretty amazing.
Yeah, 48 years, yeah.
All right, victorious Octopus in the lead. Here we go. Europa is a moon of Saturn, Mars, Neptune, or Jupiter. So Europa, the Europa Clipper is the mission that is checking that out. But is it hanging around the neighborhood of Saturn, Mars, Neptune, or Jupiter? You've got a picture clue decoding there if you need it. And you've got about 10 seconds to lock something in. All right, good job, crew. Jupiter is the correct answer. Largest planet in our solar system. It is a battle between the whimsical fox and I forgot what the victorious guys were. The victorious, well, we'll see if octopus. Victorious octopus, that's who it was. NISAR is being used to explore. Is it Earth, Venus, Mercury, or Saturn? I believe this is our final question. Is it exploring Earth, or maybe somewhere further along, like Venus, Mercury, or Saturn? Again, we've got a clue decoding to help you in those last few seconds. And then we'll take a look at our podium before we get right into that Q&A for real this time. 5 more seconds. All right, good job, crew. It is, we often think about going out into the solar system, looking at other planets, but NASA can help us learn a heck of a lot about Earth by turning those lenses back at us. Very cool. Okay, so in third place, we've got the fascinating lemur. In second place, the whimsical fox, so dethroned from the last question. All right, dramatic blobfish. Very cool. Swooping in at the last minute to take that Kahoot victory. All right, let's come back from that screen share and let's focus on Q&A action for the rest of our time together. So let's see. We've got Miss Peltier's class. Where are they joining us from? They're joining us from Maine. And they want to know, do you know, Bobak, when the first rover landed on a planet?
No, I can't. Okay, so it's a hard question. I can tell you the first successful rover, which was Pathfinder. That's or Sojourner rover, which was July 4th, 1997. But I believe the Russians landed a rover technically on the surface of Mars before that. It just didn't last. I think it basically got there and then maybe it made it like a few seconds. Um, so I can't remember what year that was.
All right. Well, Google says that it's Pathfinder, but technicality of a Russian one landing, but maybe not functioning.
Yeah.
That could be there too. Okay, very cool. We have a virtual elementary school in Ontario, Canada, hanging out with us backstage. I'm going to pop them into the call. I think we have them via audio. How are we doing today, crew?
Hi, we're doing good.
Excellent.
So we have a question. How hot is Mars?
Oh, so where we are, let me see if I remember this. We see almost as warm where Curiosity is, and I think as well as Perseverance, we see almost as warm as Earth on the day, which is about 20 degrees Celsius during the daytime. But the night times get down to, I want to say -70 or 80 or so. I can't remember off the top of my head anymore what the nighttime lows are, but they're very bad. Without the atmosphere to keep it warm, really at night, it just loses all the heat that it gains from the sun during the day.
All right. Virtual elementary, before I jump back to YouTube, do you have another one handy for us, or do you want me to check in a minute?
No, sure. We have another one.
Perfect.
What was it like watching the Perseverance land on Mars when you were there
Awesome.
live watching it?
Yeah, so I didn't fortunately, was working on something else, so I didn't have to feel the stress this time, the way I did for my own mission. So it was really great to just kind of sit back and watch it. And of course, just root my friends on, I think. But it's always exciting and it's always risky, and yeah, it just. I know what it goes into making that moment happen, right? Because it's 7 minutes of terror, as we affectionately call it, from the top of the atmosphere to the surface. But the years of people's lives that have gone into perfecting the choreography of that 7 minutes is a lot, and so I know what's on the line for them, and I know how much it means to them. So it's really exciting to just kind of cheer your friends on, and of course, in this, well, we've been so successful lately that it's kind of feels like it's not hard, but it's incredibly hard. So yeah.
All right. We'll check in with that crew shortly. And correct me if I'm wrong, Bobak, but there's a span of time too where whatever's happened has happened, and you kind of wait for that signal to come back.
Yeah. So I mean, Mars for Curiosity, the distance was about 14 light minutes away. So if you think the light from our sun takes 8 minutes to reach us, the light, or in this case, the signal from Mars took 14 minutes to reach us. And so when I talk about the 7 minutes of terror, it was already over for 7 minutes from the time that we heard the first signal that we were entering the atmosphere of Mars. So it's very much like taking a test and not knowing the results, and then just watching your score get tallied as the various parachute segments and everything else go along.
All right. I have a lot of questions about Mars here, so I'm going to put a couple of them your way. Let's see. Okay, so 2 questions about Mars. Eric wants to know roughly how long is a day on Mars, and then Xenon wants to know if the gravity is different.
Yeah, good questions. The Martian day is about 40 minutes shorter. 40 minutes shorter than our day, longer than our day. Oh, now I'm going to stop myself. I'm going to say it's long. Trying to remember which way the time moves through my nighttime. I want to say it's longer. Joe's gonna look it up, and he's gonna tell me the answer.
Yeah.
I'm gonna say it's 40 minutes.
You are right. It is about 40 minutes longer.
Yes. Okay. Good. Yeah, the fun part about that is, while that doesn't seem like much when you are working like the teams do, at least at the beginning of the mission on Mars time. It's like a 40-minute jet lag every day because you have to work during the Martian daytime, right? The rover is from the sun to work, and to basically operate the rover, which means we are basically working mostly at night on Mars to prepare everything to tell the rover to do during the daytime. So that meant that every day I would wake up 40 minutes later, which sounds like a dream, except that like my body is constantly adjusting to like a jet lag. But it does bode well that if humans or other things need to live, or move to Mars or whatever, it would be kind of similar to what we experience. And then the gravity is about a third, I think, of the Earth's gravity, and so it's it's less third, fourth. Shoot. Boy, it tells you how long I've been off Mars, is because I forget all these
It
little
would be
things.
hard moving because you focus on one planet for so long, then you spend 9 years on another
Yeah.
mission. So it does, I can imagine that you can get some of those facts mixed up when you go from mission to mission like that. Absolutely. We can double check that too, but there's kind of a fun question here. Another engineer that I know these classrooms must know from YouTube because they're wondering if you've ever worked with Mark Rober before.
Yeah, of course. Well, so Mark worked on Curiosity. We were on it about the same amount of time, and that was he worked on that, and then that was about when he decided to, when the Curiosity landed, I should say, is that when he decided to sort of go out and kind of create his own, exploration of, I guess, of engineering.
All right. Okay, so the answer I got for the gravity is we're 9.8 meters per second, and Mars is about 3.7
third
meters per second. So third, yeah.
Yeah.
All right. Great questions coming in from this crew. So you mentioned wind on Mars, storms on Mars. So Eric's wondering, is there anything that you need to do, the engineers need to do, to help the rover survive when maybe a big storm comes through?
Yeah. So there are dust storms. We see things like dust devils, for example, on the surface of Mars. For the rovers that we have, the number one thing we can do is park any optics that could get covered by dust in a way that they are less likely to. That means usually, if the head is looking out like this, we tilt it down. If there's a cover, for example, you could put the cover in place. The solar-powered rovers, it turns out, we thought initially that the dust would settle on the surface of the solar panels, and actually in the Opportunity and Spirits missions much sooner, it turns out those dust devils were actually cleaning the solar panels. So we'd actually get these dust devil events, and then they would wipe off dust that had settled basically on the surface and allow us to have more power. So fortunately, for the most part, we really haven't had to do much in terms of planning for the weather. The one thing that the solar panel powered missions and any other solar panel missions in the future would have to do is potentially angle the solar panels for winter versus summer. Because as you kind of imagine, you're solar powered and you're trying, a lot of your energy is going to keeping yourself warm, but then it's getting to winter, which means that you're getting less sun and also less heat. So you really have to make sure those rovers in those cases were parked at an angle such that the arrays would capture kind of as much sun as possible during the wintertime, so they could keep the rovers kind of heated at night. And that, in fact, is how we ended up losing, sadly, Spirit. Spirit was driving along, got a wheel stuck, and basically it was still communicating and working, albeit we couldn't get the wheel unstuck out of the sand. But when the winter came, we knew we didn't have enough power because the way it was stuck was such that the solar panels weren't going to get enough sun in the winter to keep it warm. And that was sort of the ticking clock, unfortunately, for Spirit.
All right. I want to check in with our virtual crew one more time and see if they have another question for us.
Yeah, we sure do.
Awesome.
So we're wondering, how are some of the things you're learning going to or already helping humans on Earth?
Yeah, great question. I'm real proud of NISAR. It's meant to very much be a helping us sort of thing. So one of the things I mentioned is, for example, soil moisture. Soil moisture is a big metric for a couple of really big things. One of them is agriculture. The other one is, or a couple of them is, soil moisture also helps us predict how storms will behave on landfall. So if you have which we do, our meteorological models, based on the amount of moisture available to the storm as it enters land, it can also tell you how that storm will behave as it enters land, and that'll help us sort of help warn people or predict basically where the areas that might be affected or might be more severely affected could be, and therefore ideally evacuate people early. Obviously, if not possible, at the very least, help us deploy resources afterwards. And similarly, the other thing is soil moisture can also help us with things like understanding how mosquitoes or other disease kind of carrying insects or things like that would traverse. Again, they'll be using soil moisture effectively, right, as a vector for reproducing and moving. And so we can also tell you, right, from the data how those things are occurring. But a lot of this, like I said, the agricultural stuff and the weather stuff is being used on a daily basis. And then the big things like deformation of the surface can help us see things like water movement, of course. So deformation, right, in areas where there's water tables underneath the surface can be used in real time to estimate the water volumes. Things like post-earthquake or volcanoes or things like that, we can see where, or even we can see magma flow from certain regions to other regions and therefore, right, maybe able to predict where the eruptions might occur on those volcanoes and things like that.
All right. Thanks, virtual crew. Bobak, we'll finish with one or two from YouTube. This is our class in Tucson, and they're curious. Obviously, curiosity, some days it's moving, some days it's not. But what would a big travel day be like for curiosity if it was pushed to travel?
Yeah, our best days for curiosity were on the order of about 100 and maybe 150 meters or so. And that's all because we are responsible from the ground to plan that. Perseverance can do better. So Curiosity basically had 3 modes of driving, which was what we call a blind drive, meaning that the rover was not thinking about how it's driving. We were basically planning, you turn the wheels this many times to go in that direction, and then you turn the wheels this many times to go in that direction. And then we had a couple of things where we could sense how well the wheels were turning, called visual odometry, to say, look at that rock on the ground and make sure if you turn the wheel one rotation, that the rock is now moved by the circumference of the wheel. And then there were these sort of autonomous drives where you could tell it to drive in that direction, and it would take images, pause, process them, and then decide on a safe place to go, and then drive that distance. So that's sort of the limiting factor for us, was pausing. Perseverance added another computer, which actually allows them to do the driving and processing in real time. And so they're able to drive, I think, on the order of about 200 meters in a day on their best days. Again, given good terrain, they can basically process and keep driving the whole time.
All right. And then Dominic's kind of asking, I think, the $1 million question when it comes to when we look out into our solar system, Mars, Europa, and beyond. So he's wondering if we found fossils, which if we had, that would be pretty groundbreaking. But yeah, there has been recent stories about a possible biosignature. Can you tell us anything about that?
I'm certainly not the expert in that. I think there's good evidence coming out of the Perseverance mission for chemistry that seems to need to be replaced by biological material. And so therefore they're kind of optimistic, right, that it's the most likely explanation for this would be, right, sort of a biological, I guess, impact, right? So you're looking for something that needs to be replaced, and therefore, right, that seems like the most plausible scenario in this case. There are other ways, of course, for things to arise, so you can't rule out all possibilities. And I think one of the big motivations for follow-on missions is we really want to be able to bring those samples back into the Earth laboratories, where we can more conclusively answer those questions. That's sort of the challenge, right? The carrying the laboratory to Mars and miniaturizing it is very hard. Right? It's almost easier, even though it's very complex, to take the sample there and say, let's bring it to Earth, where we could hopefully conclusively say if there was life on Mars.
All right. Well, the search continues. Personally, I think there's way too many galaxies, way too many stars, way too many planets for us to be alone. I think we've asked you this in the past. I think you're probably on board with that thought too.
Yes, 100%. I can't imagine we're alone in the universe.
Yeah, very cool. Well, Bobak, I want to start off with a huge shout out to our classrooms. Thank you for so many great questions. Thanks for playing Kahoot. Shout out to the classrooms who will tune into the recording, who couldn't make it live. Always great to have you joining us any way that you can. And Bobak, thank you so much. Thank you for making time. I know you're always busy with projects, so getting to steal this chunk of your time means a lot to us and the classrooms.
Well, thank you. I'm so excited by doing this every time. So I'm going to go hit the books and do some analysis, being really motivated by this. So I appreciate it.
All right, excellent. Well, classrooms, enjoy the rest of your week. Enjoy the holiday season. If we don't see you before Christmas, but there's still lots more coming up. So we hope to see you at least one more time. But we'll say goodbye for now. Thanks, everyone. And we'll sign off.